Okay, let's see if this is focused. Yeah, it is. Where's my camera? It's not focusing. What's going on here? Okay. All right, let me find. Get my phone. Ouch. 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 Kirsten. There you are. Okay. All right, so we'll do a little bit more implicit practice. So I've got the book here so I can pull some examples. Watch out, Ella. Move. Okay, so, you're going to have these functions that have x's and y's. And I think that what you were trying to say is that when you take the derivative, so if I take the derivative of this term, it's just 2x, right? And if I take the derivative of this term, it's 2y, and I write y prime because it's easier to write. If I take the derivative of that, it's 0. You're okay with that. Is that correct? Okay, good. Now look, the other notation, the dy dx is, for each one of these terms, I could say I'm taking the derivative of this term with respect to the variable x, plus I'm taking the derivative of the next term with respect to the variable x. And then I'm taking the derivative of this term, again, with respect to the variable x. So it's the same as y prime. It's just more work to write it, in my opinion. So the derivative, since this x matches the variable in this term, then that's why we get 2x and we're done, because we're differentiating this with respect to the variable x. They match, right? This is x and that's x. Here, it's not the case. Here, I'm taking the derivative with respect to x of this variable y. So what we really end up with is 2y dy dx. Okay, so I know it's easier to write 2y prime, in my opinion, but the y prime means dy dx. It's the same thing. It's just a different notation. And then here, the derivative of a constant with respect to x is just 0. Okay, so whether you want to write it like this or like that, it's the same exact thing. And then the goal is, for every one of these problems, is to get the y prime or the dy dx by itself, and then move everything else to the other side and solve for this thing. So in this particular example, I'd subtract 2x from both sides. So I'm left with 2y dy dx is equal to negative 2x. and then I would divide both sides by 2y, and those would cancel. And so then I'm left with dy dx is equal to negative x over y. Is that okay? You see, it was much easier. I mean, I didn't finish using the y prime over here. I mean, I just took the derivative. But if we, went on with this a little bit, it's, 2y y prime equals negative 2x. So y prime is equal to negative 2x over 2y, or negative x over y. So you're getting the same exact answer. It's just the notation here is different than here, but they mean the same exact thing. So, the reason why I'm using the dy dx the most is in related rates, and that's why I asked you, is it a related rates problem? So let's just look at an inflating balloon for a second. This is just an example from your book on page 231, so that way you can go back and reference it. We have a balloon that's being inflated at a rate of 10 pi cubic feet per second. So I know that the volume is changing, right? The rate of change of the volume. Now, this is dV dt, and I'll talk about this in a second. They're equivalent, but this is changing at 10 pi cubic feet per second. So I know what the rate of change of the volume is. With related rates, the variable down here is always t for time. So it's never going to match. I mean, it could every now and then, but most often it doesn't match the variable for what we're doing. There's not a t, right? So just as a side note, if I wanted you to take the derivative with respect to t of t cubed, well, that would just be 3t squared, right? Because this t and that t match. If I asked you to take the derivative with respect to time of x cubed, well, then you're going to have 3x squared dx dt, or 3x squared x prime. Oops. Does that make sense? So in this case here, I know that the rate of change by volume with respect to time, or v prime, if you want to call it that, is 10 pi. And they want to know at what rate, so at what rate is the radius increasing, the rate of change of the radius with respect to time when the radius is 2 feet. So spheres are really easy because the formula for volume of the sphere is 4/3 pi r cubed. So I have v and r here, I have v and r here. So I have the two variables that I need. And if I take the derivative of this function here, this formula, then I'm going to have dv dt over here, or v prime, is equal to 4 pi r squared r prime. So a lot of times you'll see me use the dr dt because those notations are, sorry about that, those notations are used interchangeably. So far, so good? So the idea is, I need to find dr dt, so that's r prime, when r is equal to 2. So I know v prime is 10 pi. That's equal to 4 times pi when the radius is 2 r prime. So that's the thing I'm solving for. So this is 4 times 4, or 16 pi on the right. And now if I divide both sides by 16 pi, the pi's will cancel over here, and then I can reduce that. So r prime, or dr dt, however you want to call it again, 2 goes in here 5, and 2 goes in 8. So the answer would be 5/8, feet per second, or whatever the units happen to be. Okay, if there's a 3xy in the equation, you're still differentiating implicitly, but you've got to use the product rule. So you've got to know your rules of derivative. So here, let me change this. So let's just do that very simple example. So we have 3xy, right? And let's just say, I don't know, y equals 3xy or something. So if I want to take the derivative, if I'm just focusing on this side, this is a constant multiple. and I have, I put the variables together. That's a product. So I have to use the product rule, right? The product rule says leave the first alone, take the derivative of the second factor, add to that the second factor times the derivative of the first, right? And if I take the derivative of this, well, I've got xy prime. That cannot change. When I take the derivative of this term, though, the derivative of x with respect to x is 1. So 1 times y, I'm going to give you y. So if it's not a related rates problem, if, you're just given something like, I'm going to write backwards here. So if you're just given something like, 2x squared plus xy equals 3 or something, and you're asked to find the derivative, well, you're always going to differentiate with respect to x, unless you're told otherwise. If it's a related rates problem, you're going to differentiate with respect to time. So generally speaking, if you're differentiating x and y, none of those variables match a t. So you're going to have a 2xx prime and a y prime in the formula. So back to this. Now I can't do anything else with this. This is done. Okay. So if it did equal to y, the derivative on the left here would be y prime, right? And so then the idea is that I got to try and get my x and y's together. Get my y primes together. So I'd say y prime is equal to 3xy prime plus 3y. And then I could subtract 3xy prime from both sides because I'm trying to get those y primes or dy dx's together. Now I can factor out a y prime, so I'm left with 1 minus 3x is equal to 3y. And now I can isolate y prime by division. And I'm done with that. Is that okay? So you're going to have to recognize the most you're really going to have with implicit is a product rule. You could have chain and other stuff, but for what you guys are doing, you won't. So the most that could happen is you'd see something like that. And then, of course, you have that one big implicit problem that I went over in the video, which would just require a lot of practice. But I confuse what dy dx is. And you can correct me if I'm thinking wrong, but if you have y equals x squared, you're taking the derivative with respect to x of y is equal to the derivative with respect to x of x squared. And over here, I can't take the derivative of y with respect to x, and that's how you end up with this little notation, dy dx. Over here, I can take the derivative of x. So once I take the derivative, that thing goes poof, it goes away. Does that help? Kirsten, you're going to ace this exam. Ace. You both will. You both do good. You'll see. Okay. So you're good now, Malia? Or do you want to do another example on anything in particular? Or Kirsten, do you have any other questions too on something else maybe while I'm here? It's kind of like teacher on demand, right? TOD, teacher on demand. Okay. So Malia, you think you're good? Good. Yeah. Practice what's on the test review. And again, related rate starts on page 231 in the book. If you want to do some of those practice problems, do the odds and check with Bob. But implicitly defined function starts on page 226. Kirsten, you're good. You don't have any other questions about anything else while I'm here? All right. Well, then, is your test tomorrow? Block 13 is test. Correct. The semester one review video, right, is less AP style and more what you're going to see on your exam. Thursday's your test. Okay, so good. So you have tonight and you have tomorrow. So, make sure you study well. And I think all of you are going to be just fine, right? Just take a deep breath and just check your work. And do the easiest problems first and go back to anything that's difficult. It's all calculator all the way. The only problem is you can't use your calculator on this. So, all right. So anyway, you guys have a good night. Thanks for stopping in, and let me know if you have more questions before your test. Capiche? All right. Thanks, guys. You're welcome. Have a good night.